Got it. Sorry, I see the chat window now. Yeah. Well, good evening. Welcome to Exploring Planetary Climate. This is the talk of a book that was published last year. I didn't manage to get the Discord thing sorted out, my fault. So if you do have follow-up questions, you'll need to track me down. I'm easy to Google, but the email is there. My mouse I'm at the Johns Hopkins Applied Physics Lab, which builds and sends spacecraft throughout the system. I'm a spacecraft engineer by training, but over the years I've become more of a planetary scientist. I work on a NASA mission at Mars, Japanese mission at Venus, and at APL I help put together the Dragonfly mission concept. I occasionally get out into the field, so it's not just all computer models and space hardware. And what I got into was planetary climate and how we understand it, and how in parallel with learning about conditions on other planets, we also figured out how our own climate works. And that's a story that basically goes back to the beginning of history. If you actually look even at Herodotus, in the 500 BC or so, he reports that there were seashells on mountaintops that suggest that the sea level was higher at some point in time in Egypt. They're trying to figure out how it is that as you go south from the Mediterranean, it gets hotter. So how can the Nile be coming from the south, and why does the Nile flow stronger in summer when it's hotter, when there's no rain? And of course, it's because of snow melt and so on. But we live on a planet. Our prosperity depends on climatological factors, navigation, agriculture, and so on. And so it's always been a feature of how we want to understand the world around us. But of course, the story really starts in the sort of after this sort of scientific revolution, and I'll really be talking about the last couple of centuries with an emphasis on the last 50 or 60 years as we've gone into the space age. And just to sort of set the stage here, this is a plot of atmospheric carbon dioxide concentration over the last 160 years, with a few of the key players kind of called out that will be going through the progressive understanding of how heat works, the recognition of the ice ages, the understanding of the greenhouse effect, and then the introduction of numerical models that let us predict the climate and how we had to adapt those to other worlds. And then, of course, the opportunity to actually visit those other worlds within our own solar system with robotic spacecraft. One of the neat things that was one of the many neat things that Edmund Halley, the astronomer, did, as well as predicting the return of the comet that bears his name, was he made the first vector map, as far as is known, to plot out, based on the reports from ship captains, the direction of the trade winds. So you can maybe just see that these little ticks have a sort of thick end and a narrower tail. We didn't, the arrowheads hadn't been invented, but this kind of plots out, the direction of the wind patterns. And this is kind of the first real attempt to put data at a planetary scale in a single framework, right? The weather isn't just what you experience at one place and one time. It's part of a bigger system, and that system has trends and patterns and repeats, and this was his attempt to grapple with it. Halley also did a lot of other pioneering things in climate, like figuring out exactly how much sunlight different latitudes got, and even did a scaling calculation. He had a pan of warm water and measured how long it took to evaporate, and kind of guessed at the area of the Mediterranean Sea, and realized that it was out of balance with the rivers flowing into it. There had to be a flow going into or out of the Atlantic. And these are just the sort of thought processes, the sort of models that we use to understand planetary processes today. As a Briton living in the USA, it's fun to recall that the ocean circulations were kind of first pointed out, recognizing the traffic between the States and Europe, and in particular Benjamin Franklin, who was a real polymath and famous for his work on lightning and so on, as the postmaster, noted that the ships going from Europe to the States took rather longer than those going in the other direction, even when the winds were factored in. And again, speaking to ship captains, he compiled information that let him lay out the existence of what we call the Gulf Stream, which is part of the broader ocean circulation, which plays a big role in moderating the effect of the different levels of sunlight at different latitudes and how they control temperature. Basically, Northern Europe would be much, much colder if it were not for the heat in the Gulf Stream. Benjamin Franklin was frequently crossing the Atlantic himself. He was an ambassador in France and observed balloon flights. One of his writings was kind of fun for me. I do some field studies on dust devils, vortex whirlwinds that pick up dust. And although they're more often found in the desert Southwest, they can appear in a lot of places. And Franklin describes an encounter with one while he's on horseback, and he tried using his horsewhip on it to disrupt it, and found that it had no effect. He also speculated that the harsh winter of 1783 was caused by the eruption of the volcano on Iceland, Laki. There's a really nice book about that called Island on Fire. But basically the sulfurous emissions of that volcano caused sulfate aerosols that basically blocked sunlight. There was a scientific conference I was supposed to go to about a decade ago that had to cancel the trip because the air traffic over the North Atlantic was disrupted by a different Icelandic volcano. In the same era, Thomas Jefferson, was a farmer as well as his more notable political work, and he recorded that climate change was happening, that snows were less frequent, and this is largely an effect of land clearing, as far as is understood. That the changing amount of trees affects the reflectivity of the ground and the moisture budget. And he even wondered whether cutting a channel through Panama might let the sea temperatures change and basically get rid of some of the fogs in Newfoundland, which is kind of the first example I've come across of speculative planetary engineering, which gets talked about these days in the context of combating greenhouse warming. Over in Russia, the first kind of indications of an atmosphere on Venus were actually noted by an astronomer observing the transit of Venus across the sun. If you look at just this little corner blown up, basically when Venus was right at the edge of the sun, and we had some transits of Venus in 2012, the disk of the sun was slightly distorted because the atmosphere acts like a little lens, and this is in fact how we have a hope of interrogating the composition of exoplanets when they let some of their starlight go through the atmosphere to our telescopes. So this was the first solid indication of an atmosphere on Venus. there had been telescopic observations of clouds and polar caps on Mars by this time. It's also interesting in a northeastern USA context to note that the platform on which the Declaration of Independence was read was actually originally erected to observe a transit in 1769, and actually reports that Benjamin Franklin published in the Proceedings of the Royal Society of London were maybe some of the first American signs reported in Europe. As the European powers of the time explored more and more of the world, they collected information more or less systematically. There's a great book you can find online, edited by the astronomer John Herschel. It's the Royal Navy Manual of Scientific Inquiry. It lays out how ships' captains or their delegates should record the weather patterns at different locations, how to write down the pronunciation of exotic languages, how to document the tidal conditions, and so on. It's a really, really fun read. But obviously there is a very systematic variation of climate with latitude, and that's a profound feature of climate on other planets as well. You can see these horizontal lines are distorted a little bit because of the ocean currents. The Gulf Stream, the thermohaline circulation lets warmth get further north in the North Atlantic. And there's also the effect of altitude, and explorers like Humboldt, who provided the basis for this map, was a great mountain climber. He explored many mountains himself in South America, and you have these climate zones where the vegetation changes as a function of altitude, and there's a trade-off between altitude and latitude. It was about in the mid-19th century that people started to consider whether mountaintops might actually be a good place to study other planets and the stars. And Piazzi Smith from Scotland, in fact, where I'm from, brought a telescope up to 9,000 feet in Tenerife off the coast of Africa, and noted that as you get higher, obviously it gets colder. That's pretty well established in all mountain ranges. But the sun gets stronger, right? So how does the sun get stronger yet it gets colder? This paradox had to be resolved. And he noticed that everyone got very suntanned, and the varnish on his barometer casing blistered. And what he's got here is a thermometer with sort of a black absorber on it, basically a means of measuring the power of sunlight, right? Until you have a measurement of that, you can't understand how the climate works. And Piazzi Smith's book is really interesting. Again, you can find it online. It's actually full of stereo photographs. This is just one of a pair, and you can get if you sort of squint right, or you have a stereo viewer, you can actually see the 3D structure of all this. He noted that even though they were 300 miles off the coast of Africa, there were sometimes big dust clouds blowing across the sea. Those, in fact, turn out to be very important in the fertilization of the oceans, and even the Amazon rainforest. The nutrient budget, the iron in particular, can be controlled by the amount of dust in the atmosphere. And he noticed that on the dustier days, there was less sunshine as measured by his instrument, but a thermometer in the shade got warmer because the dust was absorbing the heat that would normally fly straight through the thin atmosphere. And again, this is sort of just starting to get the hang of radiative heat transfer, which is the fundamental means by which heat goes in and out of planetary atmospheres. The advent of the telegraph permitted simultaneous observations of weather to be assembled into a coherent picture. And in about 1860, Joseph Henry of the Smithsonian took telegraphed weather reports and kind of compiled them instantaneously into a kind of real-time map in the lobby of the Smithsonian. And actually, this sort of idea of predicting weather by seeing weather patterns and their movement works rather better in North America than in Europe, because at these latitudes, the weather is kind of coming from the west, and the west for Europe means the Atlantic Ocean, and there aren't telegraphs there. But in the USA, you can get a report from Chicago or whatever, and guess that maybe that's going to tell you a little bit about what the weather will be like here tomorrow. William Ferrell kind of worked out this sort of trade wind pattern and its relation to planetary rotation, and again, that's fundamental. As you change the planetary radius or you change the rate of rotation, you influence the latitudinal extent of these circulation cells, and that has a profound effect on the weather. In particular, for example, on Titan, which is a small, slowly rotating body, these cells extend much further than they do on Earth. And getting this sort of big picture of atmospheric circulation kind of lets you start contemplating, voyaging around the Earth by aerial means. And there was a report in the New York Sun in 1844. It had people mobbing the newspaper offices, actually, about this report of a transatlantic balloon crossing. The funny thing is, it was actually fake news. It was a made-up story by Balzacon's own Edgar Allan Poe, in fact. He just kind of made the story up just to kind of drum up excitement. Of course, in this same era, there were occasional events that had a global impact, the Krakatoa eruption, and we'll come back to a modern counterpart a little bit later. But balloon ascents were happening. Obviously, the Montgolfier brothers were in the late 18th century, but people started flying with the intent of making scientific measurements. And there was a British meteorologist, James Glaisher, whose explorations were just dramatized in I think it was HBO movie, The Aeronauts, and the gas balloon got to probably something like 30,000 feet. The actual height wasn't properly recorded because he passed out, and his assistant managed to pull the vent cord with his teeth because his hands weren't working right. But these high altitude explorations, in the end, done automatically with sort of chart recorders, recording data on a rotating cylinder of metal with a sort of stylus that left a scratch, documented that yes, it gets colder and colder as you get higher, as was known going up a mountain, but eventually the temperature levels off. You get to what was eventually called the stratosphere, and that was all over a century ago now. What happens in the Earth is that warm air rises and cools off. That's a property of all gases. But as you get to a high enough altitude, the absorption of sunlight by, in fact, ozone in the Earth's atmosphere causes the temperatures to rise again. And the same effect happens, for example, on Titan, but it's with a different gas or a different absorber. This whole absorbing of thermal radiation and sunlight by gases had to be quantified to understand all this, and the first quality measurements were done by James Tyndall in the UK around about 1840, and part of that was enabled by electrical instrumentation, a thermopile. I love this diagram because you can just kind of see how it all works just by looking at it. Basically, this metal box here has boiling water in it, so you know what temperature it was, and it's got a black paint, so it radiates heat at the right rate. And you compare the temperature of the little detector here with the temperature of light heat from a similar box, that goes through a tube of the air of the gas that's under study. And Tyndall showed that methane and carbon dioxide and water vapor all absorb heat radiation. There was actually a lady in the United States a couple of years before who showed that carbon dioxide absorbs sunlight, which is actually a different effect. It's in a way an anti-greenhouse effect rather than a greenhouse effect, but important in the Venus climate, for example. So she speculated, perhaps incorrectly, but relevant for this topic, that if the Earth had an atmosphere with a lot of CO2 in it, maybe it would have a higher temperature, which of course it turns out to be the case, but for the greenhouse effect, not for the anti-greenhouse. You can take that thermocouple technology as it was to measure temperature electrically and measure small changes of temperature, and put one of those instruments at the focus of a telescope. And actually, for many decades, the largest telescope in the world was one in Ireland, the one on the right here. It can't point in all directions; it can only go up and down. But there was a counterpart smaller telescope, a 3-foot, which was used with one of these thermocouples to measure the temperature of the moon in the 1860s. And it really required the sort of quantitative relationship of temperature and radiant heat to be laid out before you could predict in a theoretical manner what the temperature of other planets should be, knowing how reflective they are and how far from the sun. And actually, the first person I can find who actually did that calculation was a guy called Christiansen in Denmark. He was actually Niels Bohr's advisor. This was in 1889 or so. And he predicts very cold temperatures for Mars, minus 40 Celsius, minus 30 something, not clement. Of course, not long thereafter, Percival Lowell in the U.S. Looked through a telescope and was excited at what he thought were canals, and speculated about a civilization struggling to fight cold desertification with canals. And it's interesting that this was he set up his observatory in Arizona, not far from the Grand Canyon, and there is actually now a canal called the Central Arizona Project that takes water from the Colorado and brings it south, not far away from Flagstaff, where the observatory that bears its name is. And actually, it's interesting. Lowell was a publicist, among other things. He wrote a lot of popular works about Mars, and the scientific community, predominantly in Europe, very much rounded on him for saying stuff that basically they didn't think to be true. And it's interesting just reading some of the literature of the time at how they sort of try to take apart, piece by piece, the evidence that Lowell, who basically was wishful thinking, offered. This graphic on the right is by Edward Maunder, the guy who's famous for sort of sunspots, that predicts the temperature as a function of latitude on Mars and on Earth. And I think this is the first effort to show the variation of temperature on Mars with latitude. But you can quite clearly see that his calculations indicated that it was inhospitably cold. And it was maybe in the 1920s that there started to be credible thermocouple measurements via the 100-inch Mount Wilson telescope, among others, that kind of confirmed how cold Mars actually is. Meanwhile, there were better measurements. This one by a balloon in Antarctica by a guy called Simpson in the UK. And this was really when the greenhouse effect started to be properly understood and quantified in a modern kind of manner. Meanwhile, the ice ages were kind of becoming understood. It was from 1840 that the speculations that maybe the climate really was different a long time ago came out. They were first quantified by an interesting guy called James Crowl in Scotland. He was a very unsuccessful guy at a number of careers, but he got a job as a janitor, a little bit like Goodwill Hunting, in a university in Scotland, and that gave him access to a library where he basically taught himself geology and astronomy and mathematics. And he calculated, for example, how much heat was being transported by the Gulf Stream and how much colder Northern Europe would be if it weren't there. He predicted how much less sunshine there would be as a function of latitude for different geometries of the Earth's orbit and rotation. And these changes, this geometry changes over time in a largely predictable way. Milankovitch, some years later, repeated these calculations in much more, in fact, excruciating detail. So these climate cycles driven by astronomical changes are often called Crowl-Milankovitch cycles. But as this understanding kind of progressively emerged, we could start to explain a lot of the landscape around us. This is a giant boulder in Washington State that was placed in the middle of this big flat plain by glacial dam breaking. Again, something that was only figured out in the 1920s. This area was actually used as a analog site for the Mars Pathfinder lander in 1997. Which landed at a similar sort of catastrophic flood location. There's a guy called Lewis Fry Richardson, who was an ambulanceman in World War I, who developed the theory of predicting weather by calculation. That if you break up the world into a grid and figure out how much force is accelerating a body of air and how much heat is going in and out of it, you can calculate the weather. And he did this calculation by hand, taking months, for one single day in 1910. And his manuscript on this was actually placed for safekeeping under a coal pile just behind the front lines, and was lost for a while, but fortunately was retrieved, and his book actually forms the basis for modern weather calculation. So all the pieces are sort of coming together. In the late 30s, there was a lot of amateurs in this business, called Callender, who noticed that maybe there was a bit more CO2 in the Earth's atmosphere than there had been when the first measurements were recorded. And not only was it a little bit higher, but it was consistent with how much fossil fuel should have been burned, and with the amount of temperature rise that had been noticed in a couple of locations. This was the first indications, the first coherent story of climate change, of global warming in the sort of modern context. This is not a new thing. Arrhenius in the early 1900s kind of figured it out. Guy Callender here actually saw evidence for it happening. And around about the same time, speculation began that maybe Venus had a strong greenhouse effect. And then, of course, there was World War II with radar and computers and rockets and all the tools that let us explore the planets. One of the brave efforts to do that before the space age was a French astronomer called Edwin Dollfus, who I actually had the opportunity to meet once. He's a magnificent guy. And in something that looks like it belongs for a Darwin Award, he built an observatory gondola with a telescope to get above all the water vapor and CO2 of the Earth's atmosphere to study Mars and Venus. And so there's actually good reasons for doing that with 104 weather balloons rather than one big balloon. It's a stabler arrangement. There's easier procurement. I heard the rumor that he effected descent with a small rifle to shoot out a small number of the balloons. I haven't been able to confirm that. But that was what the best that people could do before actually venturing out into space. Again, with a sort of Baltimore, Washington area theme, the first indications of a very hot Venus surface temperature were done with a radio telescope at NRL, a little bit south of where I'm sitting. And that indicated a very hot Venus, but it wasn't certain if that was the surface temperature. This instrument was actually calibrated with a transmitter that got put at the top of the Washington Monument, which I thought was rather cool. But it was spacecraft measurements that really resolved the matter, and the first interplanetary spacecraft from the US to Venus, Mariner 2, had a microwave instrument to resolve the question, and indeed it showed that Venus was intolerably hot, so it would wait for Russian landers to really measure exactly how hot. 1957, the first satellite was International Geophysical Year, which stimulated a lot of other activity like polar exploration and the start of obtaining ice cores that give us the clues about our own climate history. They were also the start of the systematic measurements of atmospheric CO2 that have now climbed to 100 ppm higher than the numbers the calendar reported. And then we really got to explore Mars by transmitting a radio signal through it from Mariner 4. We learned how thick the atmosphere was. It was much less thick than Lowell had hoped, for example. And in fact, it's thin enough that it radiates to space and allows the about 30% of its mass to frost out onto the poles. A really dramatic seasonal cycle. It looked desolate at first. The first pictures from the early Mariners just showed craters, but when Mariner 9 went into orbit, it found a lot more interesting things. There was a dust storm going on when it arrived. When that cleared, there was even evidence of rivers in the past. So that really kind of reawakened the Lowellian ideal of a wet and perhaps hospitable Mars. But Mariner also showed us layers in the polar cap. And this was about the same time that the first robust evidence that our ice ages really were driven by astronomical cycles. There were deep sea cores that showed periodicity, regular climate changes that happened at just the frequencies, just the intervals you'd expect from the astronomical effects. Viking, at the same time, 1976, gave us our in situ view of the Martian climate, very much a cold desert. There was a little bit of frost seen at the Viking 2 site, which was further north than Viking 1. This is Carl Sagan in Death Valley with one of the Viking landers for some tests. Venus's surface conditions were revealed only by these Russian landers, which look kind of crazy. They're basically pressure vessels. They're almost built like submarines. And they didn't need a parachute because the Venus atmosphere is so dense that you can just use this plate to slow your descent. And they were even able to take pictures of the surface in some of the later landers. But Venus really got set up as the sort of greenhouse boogeyman, right? A terrestrial effect taken to a planetary extreme. And that motto sort of stands today. The fourth climate in the solar system is the one I like, Titan. Voyager 1 visited in 1980, flew by, and Voyager 2 shortly afterwards. Titan has an atmosphere that's in many ways like our own. It's mostly nitrogen, but it's much colder because it's so much further from the sun. And its stratosphere is kept warm by the absorption of sunlight by this sort of brown smog, which has a lot in common with sort of the nuclear winter scenarios that were discussed around about this time, the early 80s. And the smog is made by the action of sunlight on methane. Methane acts as a condensable greenhouse gas, the same way water does on Earth. So Titan has a lot of features that are like the Earth, but different working materials, different temperature conditions. But it In the 80s, we saw evidence with Pioneer Venus that the amount of sulfur dioxide in the Venus atmosphere seemed to change, at least at the levels we could observe it. And we got kind of a taste of that ourselves with the Pinatubo eruption, which put a lot of sulfate aerosols into the atmosphere. And these actually reflected a bit of sunlight away from the Earth and caused about a Kelvin, 1 degree of temperature change. And it was around about this time that it became recognized that the dinosaurs were probably wiped out 65 million years ago by the climate effects of a meteor impact, not by the meteor impact itself, but by all the smoke and sulfate aerosols injected into the atmosphere, a lot like Pinatubo, but on a much more dramatic scale. In the mid-90s, late 90s, we got back to Mars with Mars Pathfinder, which saw this area strewn with rocks that had been, we think, driven out by a catastrophic flood. Even though Mars is usually too cold, there were at least episodes where liquid water flowed on the surface. And we've studied Mars with more and more spacecraft in the last couple of decades. There's been a continuous presence that is starting to show processes like the polar caps having changes that vary from year to year. There's a systematic erosion of some of this carbon dioxide ice, for example. And we've seen things like sand dunes moving, impact craters forming. We've had radars that have let us probe the polar caps on Mars, measure directly their thickness, and record some of the layers inside that record climate history. Really great pictures, some topography data that showing evidence of near-surface ice. That's something that was suspected but not certain 20 years ago. So we're now really getting quite a good handle on the Martian climate. We got to visit Titan with Cassini and Huygens in 2005 and subsequently. And that again showed, rocks. But these are kind of rounded rocks. They've been tumbled by a flash flood of liquid methane, in fact, and that's similarly formed these river channels. We had no right to expect this picture taken by the Huygens probe after landing. It wasn't designed necessarily to survive impact with the surface, but we got lucky. We're seeing with Cassini lots of different kind of cloud activity. The hydrological cycle is active today. We saw some areas of Titan's surface get dark after these cloud systems had been there. Basically, these clouds were dropping rain. We mapped out sand dunes over much of Titan's surface. And for a while, actually, in a great clash of observation versus theory, the weather models, the circulation models that predict winds, didn't match up with the direction that we could see the sand transport going. This is a radar image, maybe 100 kilometers across, showing these long dunes. And the dunes seem to be going in the wrong direction. But what we've since understood is that basically methane rainstorms cause strong winds in the atypical direction, let's say. And it's only the strong winds that move the sand. And so the sort of watermark left by the wind pattern only records these strong winds, which occur during the equinox season. So we're really actually starting to get models that have predictive utility at other planets. And these models also explain why most of Titan's seas in the present day seem to be in the north polar region. There's very little in the south. And that's because, like Earth and Mars, the orbits around the sun are not quite circular. The northern summer is longer and cooler than southern summer, and that has the effect of pumping the volatiles, pumping the methane to the northern polar regions. And that's true right now, but 30,000 years ago, most of Titan's liquid was probably on the other hemisphere, just as you get the ice ages on Earth and these layered terrains on Mars. So these climate changes leave their imprint in Titan's landscape. We've got many years of data now of all kinds on Mars, and there's a whole cottage industry of Mars weather modeling. and that will become important. Looking forward to human exploration one day, and there's a whole fleet of spacecraft in development or on their way or at Mars already. There'll be another couple going to Mars soon, and eventually perhaps bringing samples back. Venus has been left behind a little bit. Magellan in the early 90s was supposed to map Venus, as well as Mariner 9 mapped Mars. So we've got a lot of catching up to do, and there are efforts underway to catch up. So let's hope for that. And I'm just about out of time. I work on InSight on Mars, and actually we saw this in its solar panel currents. This is the shadow of the little moon Deimos going in front of the sun a few weeks ago. And it's these transit light curves, the way light is blocked by a planetary object, that let us get our first glimpses of the climate on exoplanets, which I don't have time to get into. So one thing to look forward to is going back to Titan in 2034 with APL's Dragonfly mission. And I'll just close by plugging the book again and some other books. And I'll see if I can look at the Q&A. There's a couple of, let's see. So I see one question. Are there significant effects on Titan's climate from it being a moon? Not really. It's far enough away from Saturn that light reflected by Saturn contributes only about 1/500th of the total sunlight and infrared radiation reaching it. It does have eclipses. During the equinox season, there are eclipses that last a few hours. I don't know if there was any evidence of that observed during the 2009 equinox by Cassini. Let's see, there's a longer question. KLX grade posed this observation question. Having studied cosmos recently by Sagan. Right, so the question is about scientific communication. In Huygens' day, this was, people wrote books and letters, and some of the publications were actually done kind of in code. They deliberately hid things in mirror writing or anagrams or so they could point to it afterwards and say, hey, look, I discovered this thing, look, I wrote it down, but they didn't want to give away all the details. It was during, I guess, the 18th century that modern scientific journals appeared with sort of systematic peer review and reporting, and Halley was actually a big player in getting that set up. But letters were obviously still a very common means of communication for Sagan in the 70s, for example. I remember getting my first email account working for the European Space Agency in 1990, working on Huygens. There wasn't a World Wide Web then, but there were text emails, and that becomes obviously a very, very quick way to share brief ideas. But the pace of collaboration has been accelerating, and the use of preprint servers for posting online stuff more or less as soon as it's figured out and written is profound. It's getting ever harder to keep up. Let's see, let me scroll up. Longitude using onboard clocks. So the whole business of astronomy was a strategic one in the 18th centuries and subsequently. So knowing your position at sea was a driver of clock technology. There were other methods explored by Huygens and others, looking at the moons of Jupiter actually as a means of effectively putting a clock in the sky. And the systematic acquisition of climate data was very much tied up with naval operations and exploration, but the physics of understanding the climate was more or less independent of astronomy and timekeeping. So I think there's not too many dots to join there. So I'm getting instructions that I should wrap up because we're at the end of time. So I do thank you for dialing in. I hope it was interesting, and maybe some of you might enjoy the book.